Welcome to module 17. In this module, we will discuss some inequalities concerning the probabilities concerning a random variable x, and we will also discuss certain inequalities for expected value of a function of a random variable. So, that is what mainly we will discuss in this module. So, let us see the setup. Setup is as follows. You are given a random variable x, you are given its distribution function f x, and suppose its probability mass function or probability density function is f x. Suppose g is a given real valued function. Now, as I told you in the last module that inequalities are the best kind of approximations for the quantities which cannot be evaluated precisely. So, inequalities provide useful estimates of probabilities or movements when they cannot be evaluated precisely. So, in this module we will discuss some useful inequalities. In fact, we will derive some useful inequalities. So, let us look at the first inequality. So, suppose g is a function from real line to 0 infinity, and suppose this function is non-negative. So, my g is non-negative, and suppose expected value of gx is finite. Then for any c greater than 0, probability gx greater than c is always less than or equal to expected value of gx by c. So, the only condition I need over here is g is non-negative. So, I have not put very unreasonable restrictions on g. G just has to be non-negative. So, let us try to see the absolutely continuous case. Let us give the proof for absolutely continuous case. So, let A is the set of all those x belonging to R such that gx is greater than c. So, A is the region where g takes value larger than c. Then expected value of gx by definition is same as minus infinity to infinity gx fxx dx. Now, I break this integral into two parts, integral a gx fxx dx plus integral over a complement gx fxx dx. You see, when I am taking this integral over a, what it means is, this means this is same as minus infinity to infinity gx fxx indicator function of x, where this indicator function is nothing but 1 if x belongs to a and 0 otherwise. That is what it means. And that follows from here, because IAX plus IA complement x is always 1. Because if x belongs to a, then x does not belong to a complement, so you will get 1 from only here and 0 from here. If x does not belong to a, then you get 1 from here and you do not get anything from here, you get 0 from here. So whatever may be the case, IAX plus a IA complement x would always be 1. So what I can do is, here I can write down this as IAX plus IA complement x, because I know that this quantity is always 1. So I write down this, and then this sum gets distributed over here, and gx fxx IAX is nothing but integral over a gx fxx integral over gx fxx IA complement is nothing but this. So, which is, now I know that this quantity is always greater than or equal to 0, because my gx is non-negative, PDF is non-negative. So, I am talking about integral of a non-negative function. Even if you include indicator function over here, that is also non-negative. So, this quantity would always be greater than or equal to 0, because I know that if function is non-negative, its integral is also non-negative. So, that is why this would always be greater than or equal to integral over a gx fxx dx. I can directly see that on the set A, gx is always greater than c. So, if I want, I can directly put here this is greater than or equal to c times integral over a xx dx. So, what I do is, first I write down this as gx IAX fxx. Now, note that this quantity is same as gx times fxx if x belongs to a, and this is 0 otherwise. But if x belongs to a, gx is always less than or equal to c. So, this quantity would be further less than or equal to c times fxx if x belongs to a and 0 otherwise. So, c fxx I can take outside, so that becomes, if you want this, you can write down as c fxx IAX. So, what you see is this quantity is always less than or equal to c times fxx IAX, or which is equivalent to saying that on set A, gx is always less than or equal to c. Gx is always greater than or equal to c. So Gx is greater than or equal to c, so that is why this is greater than or equal to c IA fxx dx. And the justification I have given, because if you write down this integral in terms of indicator function, then Gx Iax is always greater than or equal to c times Ix. Because if x belongs to A, Gx is greater than or equal to c, because here Gx and here c. If x does not belong to A, anyway both sides 0. So here what you get is, this is same as c times integrating the PDF over the set A, which is same as c times probability of A, which is same as c times probability Gx is greater than c. And this quantity was nothing but expected value of Gx. So if c was positive, so probability Gx greater than c is less than or equal to expected value of Gx by c. Here I am just emphasizing the convention which I was following, that for any set B belonging to R and any integrable function h, when I say that I am integrating over a set B hx, what it means is I am integrating hx ibx in the whole real line, where ibx is the indicator function of the set B. So that means this is same as 1 if x belongs to B, 0 otherwise. So simple proof. So what you get is, if your function is non-negative, then probability Gx is greater than c is less than or equal to expected value of this Gx divided by whatever this constant is. So let us try to see some easy consequences of this result. So let us try to prove this inequality. So what I do is, now I put a certain restriction on G. Let G be non-negative and strictly increasing. So in last result I had assumed only that G is non-negative. Here I am saying G is non-negative as well as strictly increasing function, such that expected value of G of mod of x is finite. Then for any c greater than 0, such that Gc is greater than 0, probability that mod of x greater than c is less than or equal to expected value of G of mod of x by G of c. Very useful inequality. So probability mod of x greater than c is always less than or equal to expected value of G of mod of x by G of c. Note that G is in my hand. As long as G is non-negative and strictly increasing, any G I can put it over here. In fact, I would like to choose a G which gives me a sharper bound. So let us try to see what happens. Probability mod of x greater than c. Since G is strictly increasing, mod of x greater than c happens if and only if G of mod of x is greater than G of c. So this set is same as this set. So the probabilities would be same. So probability that mod of x greater than c would be same as probability that G of mod of x is greater than G of c. But by the last result, because G is non-negative, so this would be less than or equal to expected value of that function divided by whatever that constant is. Because last result we had said that if h is non-negative, then probability that hx is greater than c is less than or equal to expected value of hx. In fact, you can put it here where hx is greater than or equal to d. And that is what I am doing over here. Expected value of this quantity divided by whatever that constant is. This again is a very useful inequality. We will see some very interesting consequences of this inequality. So one thing is, I take my Gx to be x to power r, where r is quantity greater than 0 and x is in 0 to infinity. So what is happening to my G? G is strictly increasing in 0 to infinity. So I take that over here, so that becomes probability that mod of x greater than c is less than or equal to expected value of mod of x to power r divided by c to power r, provided of course expectation exists. Let us see some more consequences. One thing is, for r is equal to 1, the last inequality gives, suppose that expected value of mod of x is less than infinity, then probability mod of x greater than c is less than or equal to expected value of mod of x by c. So in the last example, just take r is equal to 1. Now this inequality is famously known as Markov inequality. Let us do another famous inequality, which is called the Chebyshev's inequality. Let x be a random variable with finite mean mu, and suppose it also has a finite variance sigma square. Then for any epsilon greater than 0, probability that mod of x minus mu is greater than epsilon sigma would always be less than or equal to 1 upon epsilon square. So if I write down this probability as 1 minus probability that mod of x minus mu is less than or equal to epsilon sigma, I get from here probability that mod of x minus mu is less than or equal to epsilon sigma would be greater than or equal to 1 minus 1 upon epsilon square. So let's try to prove this result. So I prove the corollary, I use the corollary 2. What it says corollary 2? Probability that mod of x is greater than c is less than or equal to expected value of mod of x to power r divided by c to power r for any r greater than 0. So I take r is equal to 2. So we have probability that mod of x minus mu greater than epsilon sigma is less than or equal to mod of x minus mu whole square. So in place of x I take mod of x minus mu. In place of x I take x minus mu. So this is less than or equal to x per mod of x minus mu, r is equal to 2, so square divided by c square, c is epsilon sigma, which is epsilon square sigma square. But this quantity is same as expected value of x minus mu whole square, because this is anyway positive, so whether you put mod or don't put mod, it's same. But x per x minus mu whole square is same as variance of x. So variance of x divided by epsilon square sigma square. But variance of x, I have taken it to be sigma square, so sigma square gets cancelled and you get 1 upon epsilon square. So we have got this inequality or equivalently this inequality. Let us try to see some very interesting consequences of this inequality. So what it says probability that, so let me write down this inequality over here. So what we have is probability that mod of x minus mu is less than or equal to epsilon sigma is greater than or equal to 1 minus 1 by epsilon square. This is what the Chebyshev's inequality says. This is equivalent to saying that probability that x minus mu lies between minus epsilon sigma less than or equal to epsilon sigma is always greater than or equal to 1 minus 1 by epsilon square, which is equivalent to saying that probability that x lies between mu minus epsilon sigma less than or equal to mu plus epsilon sigma is always greater than or equal to 1 minus 1 upon epsilon square. So what I do is, to begin with, I take epsilon is equal to 2. So probability that x lies between mu minus 2 sigma to mu plus 6 sigma would be greater than or equal to 1 minus 1 by 2 square, and if you look at this quantity, this turns out to be 0.75. Then I take epsilon is equal to 3, so probability that x lies between mu minus 3 sigma to mu plus 3 sigma would be greater than or equal to 1 minus 1 by 3 square, which is nothing but 1 minus 1 by 9, and if you calculate it, it turns out to be approximately something less than 0.88. So this would be something bigger than 0.88, so this quantity would always be greater than or equal to 0.88. So very interesting observation. What it says, if you look at any random variable x, then the probability that it will lie within 2 sigma units from its mean, that probability is always greater than 0.75. Similarly, what this observation says is, if you look at any random variable x, the probability that it will lie within 3 sigma from its mean, that probability is always greater than or equal to 0.88. So that means for any random variable x, if you look at the 3 sigma distance from the mean, the probability that x would lie within that interval is very high, which is greater than or equal to 0.88. So let us see how sharp these inequalities are. So for example, let us try to see how sharp is Chebyshev's inequality. And we'll see that Chebyshev's inequality sometimes can be very sharp. So let x be a random variable with probability mass function given by this: 1 by 8 if x belongs to minus 1, 1, 3 by 4 if x is equal to 0, and 0 otherwise. Let us look at mu is equal to expected value of x, which is same as 1 by 8 times minus 1, 1 by 8 times 1, plus 3 by 4 times 0. So if you sum it, the mean turns out to be 0. Let us look at sigma square. Sigma square is same as variance of x. Now since mean is 0, so variance of x would be same as x per of x square. X per of x square would be same as minus 1 whole square multiplied by the probability 1 by 8 plus 1 square multiplied by the probability 1 by 8 plus 0 square multiplied by the probability 3 by 4. So if we sum it, this turns out to be 1 by 4. So what I do is I apply the Chebyshev's inequality for epsilon is equal to 199 by 100. If I do that, I get probability mod of x minus mu is greater than epsilon sigma is less than or equal to 1 upon epsilon square. 1 upon epsilon square is nothing but 100 square upon 199 square, which is same as 0.25252 approximately. So in this case, Chebyshev inequality says that probability that mod of x minus mu is greater than epsilon sigma would always be less than or equal to this quantity. Let us now try to calculate the exact value of this probability. We have seen that this bound is 0.25252. So let us try to see the actual probability. We have seen that mean is 0. So probability mod of x minus mu is greater than epsilon sigma is same as probability that mod of x, because mu is 0. Sigma is half. Epsilon is 199 by 100. So this becomes probability mod of x greater than 199 by 200. 199 by 200 is slightly quantity less than 1. So this same as mod of x is greater than this thing. So that would correspond to x is only taking value 0, minus 1 or 1 with probability 1. So the only values which will correspond and will have a positive probability is x equal to minus 1 and n 1. So which is same as x belonging to minus 1 1, which is 1 by 4, which is same as 0.25. And you know that 0.25 is less than or equal to 0.2525, which you obtained using the Chebyshev inequality 0.25252. So you can see this is very close. The bound given by the Chebyshev inequality is very close to the exact value.